We let go of things and they fall. We see them fall. We assume that seeing them fall means we know where they went, that we could follow them if we wanted to, that the path they took is still there, still real, still something we could trace back if we needed to. We don't usually check whether that assumption holds everywhere. There's something we do all the time without thinking about it. We assume that when something moves away from us, we can still see it, or at least we could see it if we looked at the right moment, in the right direction. A car drives down the street. It gets smaller. It turns a corner. And we know it's still there even though we can't see it anymore. We know this because we've seen cars turn corners before. We've walked around corners ourselves. We've confirmed over and over that things don't stop existing just because they're out of view. The whole idea of distance, of something being far away, depends on this. That you could in principle go there. That light from there could in principle reach here. That the space between here and there is still space in the normal sense, still something you could cross, still something that connects rather than separates. We rely on this constantly. When we look up at the sky, we're seeing light that traveled to us. When we remember where we put something, we're assuming the room it's in is still connected to where we are now, that we could walk back to it, that it occupies a place we could return to. The whole structure of knowing where things are, of confirming they're still there, of checking on them later, depends on the idea that space connects things, that paths through space are real and reversible, that there and here are positions in the same continuous fabric. This feels so obvious that we rarely say it out loud. It's just how space works, how distance works, how location works. Except there's a place where this stops being true. When you drop something, it falls. A cup, a book, your phone if you're not careful. It moves toward the floor and the movement has a kind of simplicity to it. It's going down, toward the ground, toward the center of the earth technically, though we don't usually think about it in those terms. The earth is pulling on it. That's what we mean by gravity. At least in the simple version we carry around in our heads. The earth has mass, the object has mass, and there's a pull between them. The earth is much more massive, so the object falls toward the earth rather than the other way around. If you throw the object, it still falls, it just takes a curved path. If you throw it harder, the curve gets wider. If you could throw it fast enough, the curve would be so wide that it would miss the earth entirely. It would just keep going, curving around and around, or curving away altogether. That speed exists. It's called escape velocity, and on Earth it's something like 11 kilometers per second, which is far faster than anything we can throw by hand. But it's a real number, a real threshold. Reach that speed, and you're no longer bound to the Earth. You're free. You've escaped. The threshold exists because the Earth has a certain amount of mass packed into a certain size. If the Earth were smaller, denser, the pull at the surface would be stronger. The escape velocity would be higher. You'd need to move faster to get away. If the Earth were larger, more spread out, the pull would be weaker. The escape velocity would be lower. You could leave more easily. There's a relationship there between mass, size, and the speed needed to escape. You can keep adjusting those numbers. You can imagine making the Earth denser, smaller, more compressed, and watching what happens to the escape velocity as you do. It keeps going up. At some point, if you compress enough mass into a small enough space, the escape velocity reaches the speed of light, which is already the fastest anything can go. And then, if you compress just a little further, the escape velocity exceeds the speed of light, which means there's no speed fast enough to escape. Not for objects, not for light, not for anything. That's when something strange happens, though strange might be the wrong word. It's not strange in the sense of being mysterious or inexplicable. It's strange in the sense that the familiar rules, the ones we've been using, start behaving in ways we didn't expect. Because if escape velocity is higher than the speed of light, then nothing can escape. Light always moves at the same speed. It can't go faster. It can't try harder. It just moves at the speed it moves. And if that speed isn't fast enough, then it can't get out. Which means that if you're looking at this object from the outside, from a safe distance, no light is coming back to you. No information is coming back to you. The region has gone dark. Not because something is covering it, or because the light is being absorbed by a surface, but because the paths that light would normally take, the straight lines it follows through space, have curved so much that they no longer lead outward. They curve back. They fall. Every direction that used to mean away from the center now bends back toward the center. The geometry has folded in on itself in such a way that outward isn't a direction anymore. We usually think of falling as something that happens to objects, to things with weight, with mass. But light falls too. This isn't new. We've known this for a long time. Light passing near the sun bends slightly, follows a curved path, because the sun's mass warps the space around it and light follows that warping. We've measured this. We've seen it during eclipses, when stars near the sun's edge appear shifted from where they should be, because their light curved on its way to us. This is just geometry. Space curves near massive objects, and light moves through that curved space. Usually the curvature is gentle. Light bends a little, but it still gets through, it still escapes. But if the mass is compressed tightly enough, if the curvature becomes steep enough, then the bending becomes extreme. The light curves so sharply that it never makes it out. It spirals inward. It falls, the same way a dropped object falls, except there's no floor to catch it, no ground to hit, just a center it keeps falling toward. Forever, or at least for as long as forever means anything in that kind of geometry. There's a boundary where this happens, a distance from the center where the escape velocity crosses the speed of light. Inside that boundary, nothing escapes. Outside it, things can still leave if they're moving fast enough or far enough away. The boundary itself is called the event horizon, and it's not a thing. Not a surface you could touch or see. It's just a location, a radius, a place in space where the geometry tips from escape is possible to escape is not possible. If you're outside it, you can still see light from objects near it. You can still receive information. If you're inside it, you can't send information out. You can't send light out. Every direction you might try to move, every path you might try to take, curves back inward. The future, in a very literal and physical sense, only points toward the center. There's no version of forward in time that leads back out. This isn't something we're imagining. We've seen these objects. Not the inside, obviously, because nothing from the inside can reach us. But we've seen the region around them. We've seen gas and dust spiraling inward, glowing as it heats up from friction and compression, sending out light and radiation as it falls, until it crosses that boundary and disappears. We've seen stars orbiting around points in space that seem empty but clearly aren't, moving so fast in such tight orbits that we can calculate the mass they're orbiting around, and finding that the mass is enormous, far too large, far too concentrated to be anything else. And a few years ago, a network of telescopes looked at one of these objects, one of the largest we know of, sitting at the center of a galaxy millions of light years away, and they saw something remarkable. They saw a ring of light, bright and glowing, surrounding a dark circle. The light was from matter still outside the boundary, still able to send signals to us. The darkness was the boundary itself, not a shadow cast by something solid. Just the absence of any signal, any information from that region. A place where the light that would normally reach us simply doesn't, because it can't, because the paths it would need to follow have been bent too far inward to ever lead back out. So we're looking at something real here. We're sitting on our porch, looking out at the night, and somewhere out there, scattered across the universe, are these regions where the basic assumption we started with, the assumption that we can see where things are, that we can trace where they went, that paths through space are reversible, just quietly stops working. You can fall toward them, but you can't see inside them. You can't check what happened to the things that fell in. You can't confirm they're still there in any meaningful sense, because confirmation requires information, and information requires light, or particles, or some kind of signal, and signals require a path that leads from there to here. And past that boundary, those paths don't exist anymore. The connection has been severed. The space between here and there has stopped being the kind of space that connects. It's worth sitting with that for a moment. The idea that there could be a place you can't see into. The space itself has curved in such a manner that looking simply doesn't work anymore. We're used to obstacles, walls, fog, distance, darkness, things that block our view temporarily, things we could get around if we tried hard enough, if we moved closer, if we waited for conditions to change. A mountain blocks the view of what's behind it. You walk around the mountain. Fog obscures the road ahead. It clears eventually, or you wait, or you use other methods to navigate. Even darkness is just the absence of light for a moment, something that changes when the sun comes up, when you turn on a lamp. These are all temporary, local, specific to circumstances. This is different, though the word feels inadequate. This is about the way space itself is shaped near a very dense, very massive object. The paths that light would normally take, the straight lines it follows when nothing is interfering. Those paths have become paths that curve back, and once they curve back, they stay curved. The geometry is what it is. If you're far enough away, you're fine. You're in a region where space is curved, maybe a little bit, enough to bend starlight slightly, enough to affect orbits, but still curved gently enough that light can propagate outward. Signals can still reach you. Information can still travel. But if you're too close, if you've crossed that threshold, that specific radius where the curvature tips over into, I'm not sure what to call it, something more extreme, then the light you emit, the signals you send, the information you represent, all of it falls inward. You could shine a flashlight. The light would leave the flashlight. It would move at the speed light always moves, but the path it travels would curve and keep curving, and eventually loop back toward the center. It wouldn't reach anyone outside. The geometry doesn't allow for it. Maybe it helps to think about movement. If you're standing on Earth and you throw a ball straight up, it goes up for a while, slows down, stops, falls back down. That's normal. That's expected. The Earth is pulling on it the entire time, and eventually the pull wins. Throw the ball faster, it goes higher before falling back. Throw it at exactly escape velocity. It doesn't fall back. It just keeps going, getting slower and slower as the Earth's pull weakens with distance, but never quite stopping, never quite turning around. That's the threshold. Below that speed, the ball returns. At or above that speed, it doesn't. Now imagine you're standing on an object where escape velocity is the speed of light. You throw the ball. Well, you can't throw anything at the speed of light, we can't, but suppose you could. The ball would escape. Barely. Right at the edge. But if escape velocity is even slightly higher than the speed of light, then there's no speed you can throw the ball that will let it escape. Every trajectory it could possibly take curves back down. Light behaves the same way. It's always moving, always traveling at the same speed, but it follows the curves of space. And if the curves are too steep, if they bend back too sharply, the light's trajectory never makes it out. Out isn't a direction the local geometry supports anymore. From the outside, from where we're sitting, this looks like a region that's gone dark. No light is coming from it. No signals are emerging. It's silent, though silent is probably the wrong word. It's more like it's stopped sending any information. It's stopped participating in the network of signals and reflections and confirmations that we use to know what's happening in distant places. It's been cut off by the shape of space itself. There's something almost ordinary about it, if you sit with it long enough. We're used to the idea that gravity pulls things down. That's just what gravity does. We're less used to thinking about gravity as something that curves space. But the math is the same. The predictions are the same. The effects are the same. When we say the Earth pulls on the moon, we could just as easily say the Earth curves space and the moon follows that curvature. Same phenomenon. The moon is moving in a straight line as far as the moon is concerned. It's just that the straight line it's following is curved by the Earth's presence. This is true for everything. For planets, for light, for any object moving through space near a massive object. Space curves. Motion follows the curvature. Usually the curvature is gentle enough that we don't notice it unless we're looking carefully, unless we're measuring things precisely. But it's always there. And if the mass is large enough, compressed tightly enough, the curvature becomes extreme. Steep. Sharp. Enough that the paths curve back on themselves. When we look at these objects from the outside, we can see the effect. We can see light bending near them. We can see matter spiraling inward, orbiting closer and closer, until it crosses some threshold and we stop seeing it. We can measure the mass, calculate where that threshold should be, find that it matches what we observe. The predictions line up with the measurements. The geometry works out. We can even see faintly the shape of the region. The boundary itself doesn't emit light, obviously it can't, but the space around it where light is still escaping, where matter is still visible, there's a kind of glow there. A ring of light from material that's falling in but hasn't crossed over yet, heated to enormous temperatures by friction and compression, radiating in wavelengths we can detect. And inside that ring, there's darkness. A circular region from which no light, no information, no confirmation of any kind reaches us. There's something we can't really get around here. If nothing can come out, if no signal can escape, then how do we know what's inside? We don't. We can't. The usual sense of knowing depends on receiving information, on detecting signals, on measuring things. We can predict what the equations say should be inside. We can extrapolate from the behavior of objects near the boundary. We can run simulations, make models, test them against indirect observations. But we can't check directly. We can't send a probe in and have it report back. We can't shine a light inside and watch where it goes. The boundary is one way. Information flows in, it doesn't flow out. And without information flowing out, we're left with predictions, with theory, with mathematical models that seem consistent with everything we can observe from the outside, but which describe a region we cannot verify, even in principle. That's the limit we're looking at. The usual relationship between here and there, between observer and observed, has broken down. We can see the boundary, or at least we can see where it should be, based on where things disappear, where the darkness begins. We can see things approach it, but we can't see past it. The connection has been severed, quietly, geometrically. By the way, mass curves space when compressed past a certain point. There's something else that happens near that boundary, something we can actually see from where we are, sitting safely far away. Light changes as it climbs out of the curved space around these objects. It gets stretched, the wavelength gets longer, shifts toward the red end of the spectrum, which is why we call it redshift, though the name makes it sound more dramatic than it is. It's just light working harder to escape in a sense, though that's probably not the right way to think about it either. Photons climbing up through a steep gravitational curve, and by the time they reach us, they've been stretched thin. They arrive with less energy than they left with. This happens around any massive object, technically. Light leaving the surface of the sun is very slightly redshifted by the time it reaches us, though the effect is so small, we barely notice it unless we're measuring carefully. Light leaving the surface of a white dwarf, which is much denser, much more compact, is redshifted more noticeably, and light leaving the region very close to one of these boundaries, close to an event horizon, the redshift becomes enormous. The closer the light originates to that threshold, the more stretched it becomes by the time it escapes, if it escapes at all. So if we're watching something fall toward the boundary, watching it from a distance, we see its light getting redder and redder as it gets closer. The photons that reach us are increasingly stretched, increasingly depleted of energy. The object appears to dim. It fades, and as it approaches the boundary itself, as it gets closer and closer to that radius where escape becomes impossible, the redshift becomes extreme. The light is stretched so much that it's barely light anymore. The wavelengths get longer and longer. The energy gets lower and lower, and eventually the photons are so stretched, so depleted, that they become undetectable. The object fades to darkness, from our perspective. It doesn't cross the boundary and wink out suddenly. It just fades, gets dimmer, redder, fainter, until we can't see it anymore. But that's just how it looks to us, from our perspective, far away, safe in relatively flat space. The object falling inward doesn't experience this the same way. From its own perspective, from the perspective of someone or something falling toward the center, the light it's emitting still looks normal, still has the same wavelength, the same energy, the same color. The stretching, the redshift, that's something that happens to the light as it climbs back out to us, a consequence of the difference in gravitational curvature between where the light is emitted and where we're observing from. The falling object doesn't see itself fading. It just sees itself falling, moving inward, following a path that feels, from its own perspective, like any other path through space. There's something similar with how time behaves near these regions, though similar might not be quite the right word. We've known for a while now that time runs at different rates depending on where you are in a gravitational field. Clocks at higher altitudes, farther from the Earth, tick slightly faster than clocks at sea level. The difference is tiny, measurable only with very precise instruments, but it's real. GPS satellites have to account for it, or their positioning calculations would drift out of alignment. This is just general relativity doing what it does, space and time being part of the same geometry, and when space is curved by mass, time is affected too. The stronger the gravitational field, the slower time runs, relative to someone farther away in a weaker field. Near an event horizon, this effect becomes, I'm not sure how to describe it without making it sound more dramatic than it is. If we're watching an object fall toward the boundary, we see its clock running slower and slower relative to ours. From our perspective, the object takes longer and longer to move each additional increment closer to the threshold. It's still falling in its own reference frame, still accelerating inward, but from our perspective, distant and external, watching the fall happen, time for the object is dilating, stretching, each second of its experience corresponding to more and more of our seconds. The closer it gets to the boundary, the more pronounced this becomes. As it approaches the horizon itself, it appears to us to slow down asymptotically, getting closer and closer and closer. But from our perspective, it never quite reaches the boundary. It just keeps getting dimmer, redder, slower, until it fades from view entirely. We lose sight of it before we ever see it cross, which creates a kind of divide. The falling object, from its own perspective, doesn't experience any slowing down, doesn't experience any fading. There's no dramatic moment of crossing. It just keeps falling, following its trajectory inward, and at some point, it crosses the event horizon without noticing anything particularly special about that moment. The geometry on either side of the boundary is continuous. There's no wall, no barrier, no physical marker indicating you've just crossed the point of no return. It's just a radius, a coordinate, a location in space where the escape velocity equals the speed of light. From the outside, though, from our perspective, the crossing never happens, or at least we never see it happen. We see the object approach, fade, and vanish, but we can't observe the crossing itself. We can calculate that it must have crossed, based on the trajectory, based on the equations, but observing it directly, that's not something the geometry allows us to do. It's hidden from us by the combination of redshift and time dilation as seen from the outside. So both descriptions are true in their respective reference frames, but they're incompatible in a way that's hard to reconcile. When did the object cross the horizon? From its perspective, at a specific moment in its own time. From our perspective, never, or at least not in any finite amount of our time that we could measure. Both answers are correct within their own context. The geometry allows for both. But it also means that there's no shared reference frame that includes both perspectives once the object gets close enough to the boundary. No universal now that we and the falling object both inhabit. We can see traces of this in actual observations. Matter orbiting close to these boundaries, gas and dust spiraling inward, the light from that matter behaves exactly as the equations predict. Redshifted severely, dimmed, smeared out in time. There are observations of stars orbiting very close to the supermassive black hole at the center of our galaxy, stars moving fast enough, close enough, that their light shows measurable redshift and time dilation effects as they swing past the boundary. The data matches the predictions. The geometry works the way the math says it should. This isn't speculative, it's observable. We're looking at the consequences of extreme space-time curvature in real time, or at least in the stretched, delayed, redshifted version of real time that reaches us from those regions. But even with all that, even with the observations lining up with the predictions, there's still this gap, this limit to what we can see. Things approach the boundary. They fade. We can calculate that they must have crossed, must have continued inward. But we can't see the crossing. We can't see what happens after. The information about that, the light from those events, the signals that would tell us, yes, this happened, here's what it looked like. Those signals are trapped inside the boundary. They're moving inward along with everything else. They can't climb back out to us. So we have this picture. From out here, far away, we see a dark region surrounded by glowing matter. Things spiraling inward, getting brighter as they heat up from friction and compression, then fading as they approach the boundary, disappearing before they cross, at least from our perspective. The space around the boundary is warped and distorted, bending light from objects behind it, creating a kind of gravitational lens effect. We can measure the mass, calculate the radius where the boundary should be, confirm that nothing emerges from inside that radius. The darkness itself, though, remains opaque, silent, a region from which no information returns. We're looking at a limit imposed by the geometry of space-time, by the way mass warps space when it's concentrated past a certain point. And that limit isn't something we can work around or see past. It's just there. The matter that falls toward these boundaries, the gas and dust spiraling inward, it doesn't just disappear quietly. It builds up. It crowds together as it gets closer, and the space it's moving through is getting more compressed in a sense, and the material starts to collide with itself, friction between particles, compression heating everything up to enormous temperatures. This is where most of the light we see actually comes from, the glowing ring around the darkness. The accretion disk, though that name makes it sound more organized than it really is. It's matter falling in, piling up, heating up, radiating energy as it goes, until it crosses the threshold and stops radiating anything we can detect. The temperature gets high enough that the matter emits X-rays, which is part of how we first started finding these objects, back when we weren't entirely sure they existed. We'd point X-ray telescopes at certain regions of the sky and find sources of X-rays that were incredibly bright, incredibly compact, too bright and too small to be explained by normal stellar processes. And when we looked more carefully, when we measured the spectra, when we tracked the motion of nearby stars, we found that these X-ray sources were associated with objects that had far too much mass in far too small a space. Objects that fit the profile, dark, compact, massive. The X-rays were coming from the material around them, the material that hadn't crossed yet, that was still outside, still visible, still able to send signals to us. We can learn things from watching that material, how fast it's moving, how hot it's getting, how the light from it is being distorted by the curved space nearby. We can trace the orbits of gas clouds as they spiral inward, map out the gravitational influence of the central object, calculate its mass based on how strongly it pulls on the surrounding material. Sometimes we can even detect slight wobbles in the orbits that tell us about the rotation of the object itself, about whether it's spinning and how fast. All of this is indirect, though. We're measuring everything around it and using that to infer what must be there, what must be causing these effects. There's a certain kind of mapping that happens here, though mapping might not be quite right. We're mapping the absence, in a way, or at least we're mapping where things stop being visible. We can see where matter disappears. We can see the radius inside which nothing emits light anymore. We can trace the edge of the darkness and confirm that it matches the predictions, that it lines up with where the event horizon should be based on the mass we've calculated. The 2019 image of M87, the one that showed the dark circle surrounded by the glowing ring, that was essentially this, a map of where information stops coming from. The resolution wasn't perfect. The image was blurry in the way that images at that scale and distance always are. But the dark circle was there, right where it should be, the right size, the right shape. We were looking at the shadow of the event horizon, the silhouette of a region from which no light escapes. Even with that image, though, even with all the measurements we can make of the surrounding material, there's still this fundamental gap. We can map the boundary from the outside, confirm that it exists, that it's where we expect it to be. But seeing past it, that's something the geometry doesn't allow. Every method we have for learning about distant objects depends on receiving signals from them, and the signals from inside the boundary simply don't reach us. The geometry forbids it. I wonder sometimes if this feels different from other kinds of unknowns. There are plenty of things we don't know because we haven't measured them yet, because we don't have the right instruments, because the phenomena are too far away or too faint or too complicated. Those unknowns feel temporary, in a way, like they're just waiting for better technology or better methods or more time. This seems different. This is a place where the information we would need to verify our predictions cannot reach us. The boundary is observationally absolute. There's no clever workaround, no future instrument that will let us see inside, because the structure of space-time itself prevents it. We have theories about what happens inside, of course. General relativity gives us equations that we can extend past the event horizon that describe mathematically what the geometry should be like further in, closer to the center. The equations predict that the curvature continues to increase, that space continues to curve more and more steeply, until at some point the equations break down entirely, until they produce infinities and singularities that suggest we've reached the limit of what the theory can describe. Testing those predictions directly, though, we can't send a probe inside to measure the curvature and report back. We're extrapolating from what we can observe on the outside, extending the math inward, trusting that the patterns hold, but without any way to confirm. So there's this asymmetry. What happens outside the boundary, we know with reasonable certainty. We've measured it. We've watched stars orbit these objects. We've seen the light from infalling matter behaving exactly as predicted. We've mapped the shadow. The external geometry is well understood, well tested, consistent with observation. The internal geometry, though, that's theoretical, predicted, mathematically consistent with the external behavior, but fundamentally unverifiable. We have models, equations, simulations that show what the curvature might look like deeper in, and they're extensions of our mathematical framework, and that extension is different somehow from the direct confirmation we get through observation, though I'm not sure I can quite pin down why that distinction feels important. There's also the question of what happens at the very center, at the point the equations call a singularity, where the curvature becomes infinite, where density becomes infinite, where the math stops making sense. General relativity predicts that all the infalling matter eventually reaches this point, that it gets compressed down to infinite density and zero volume, which is clearly something our theory can't actually describe. Infinite density isn't a physical thing we can measure or understand. It's a sign that the theory has reached its limit, that we're missing something, that we need a better description that incorporates quantum mechanics or some other framework we haven't fully developed yet. Observing the center, though, checking whether the singularity is real or whether it's just a mathematical artifact, the event horizon shields it from view. Everything that would tell us what's actually happening there is trapped inside, unable to send information back out. The boundary itself is observationally confirmed, measurably real in the sense that we can see its influence, trace its location, map its shadow. Everything beyond the boundary, though, is extrapolation. We can say the equations predict certain things, and the equations have been reliable for everything we can check from the outside, so maybe they're reliable on the inside too. Maybe. The distinction feels important somehow, between what we've observed and what we've calculated should be there. The part inside the boundary is permanently beyond our ability to verify directly, and that's unusual, I suppose. Confidence in the math, in the internal consistency of the theory, in the way it matches everything we can observe from the outside, that's one kind of knowledge. Direct confirmation through observation, seeing it yourself, checking it against reality, that's another kind. And here we only have one. We're sitting on our porch, looking out at something that's definitely there, definitely real, definitely affecting everything around it in measurable ways. We see its influence on the matter spiraling inward, the way it bends light from objects behind it, the gravitational pull on nearby stars. The boundary is there, where the darkness begins. The region inside that boundary, though, remains hidden. The darkness is imposed by the geometry, by the way space curves past a certain threshold so that information can only flow inward, and there's no getting around that. No workaround we can imagine that would let us see past it. There's only watching from the outside, observing matter spiral inward and disappear, calculating where the boundary should be and finding that the calculations match what we see, and accepting, I suppose, that some things exist in a way that prevents us from verifying them directly. The limit is built into the structure of how space and time and mass relate to each other, and it's permanent in a way that other limits we encounter tend not to be. We're used to limits we can work around eventually, but this one seems to stay. There's something about the one-way nature of this boundary that feels worth sitting with for a moment. The idea that you can cross it, that matter can cross it, that information can cross it, but only in one direction. Inward. Once you're past that threshold, once you've crossed that radius, every path forward in time, every possible trajectory you could take, curves back toward the center. There's no path that leads outward anymore. The geometry simply doesn't provide one. It's almost like, I'm trying to think of a comparison that doesn't make it sound more mysterious than it is. It's like standing on a hillside where every direction you can walk slopes downward, though that's just an analogy for what's happening with space itself, where the curvature is so steep that even light, which always moves at the same speed, which always takes the straightest possible path through space, even light can't climb back up. We're used to thinking of motion as something we have choices about. You can turn around, you can change direction, you can reverse course. Even if something is pulling on you, like gravity pulling you toward the earth, you can resist it, you can climb upward, you can move against the pull if you have enough energy. But past the event horizon, there's no amount of energy that would let you move outward. Every possible future you could have, every moment that comes next, is closer to the center than the moment before. The future only points inward. That's what the geometry enforces. Outward isn't a direction time flows in anymore, at least not in that region. And the thing is, this happens continuously. You cross the boundary smoothly, the geometry on one side connected to the geometry on the other side. The curvature has been getting steeper. The gravitational pull has been getting stronger. And at some point you pass the radius where the escape velocity equals the speed of light. And from that point on, escape is no longer possible. But you don't feel that moment arrive. You don't notice it happening. The transition is seamless, continuous, just another increment in the fall. You just keep falling, and the space around you keeps curving, and you're still following the same kind of path you were following before, just in a region where all paths lead the same direction now. From the outside, though, we never see the crossing happen. We see the object approach, we see it fade, we see it disappear, but the actual moment of crossing is hidden from us by the extreme time dilation and redshift. The light from that moment is stretched so much, delayed so much, that it never reaches us in any meaningful way. So there's this permanent divide between the two perspectives. The object experiences the crossing at a specific moment in its own time. We never observe the crossing in our time. Both are true, both are consistent with the geometry, but they're incompatible in a way that makes it hard to think about when the crossing happened in any absolute sense. There's no universal now that includes both perspectives once the object gets close enough. I keep coming back to the idea of information. Everything we know about distant places depends on information traveling from there to here. Light, radio waves, particles, anything that carries a signal. And information, as far as we understand it, can't travel faster than light. It moves through space at finite speed, following paths determined by the curvature of space. When space is flat, or nearly flat, information can propagate in all directions. Signals can go out, signals can come back. But when space is curved steeply enough, when the geometry tips past that threshold, information can only propagate in certain directions, inward, toward the center. There are no paths for information to follow that lead back out. The geometry has closed off that possibility, which means that anything that crosses the boundary takes its information with it. Whatever state it was in, whatever configuration, whatever history it carried, all of that falls inward and stays inside. Retrieving it becomes impossible. Checking on it after the crossing, confirming what happened to it, trying to verify its state or trajectory. The geometry prevents all of that. The information is still there, presumably, still part of the physical system inside the boundary, still existing in some form. But it's causally disconnected from us. Signals back to us are geometrically forbidden. It's part of a region of space-time that we can't interact with anymore, even in principle. This raises some strange questions, though strange might not be the right word. Questions about what it means for something to exist if we can't interact with it in any way. We saw it fall in. We have a history of interaction with it up until the point it crossed the boundary, so we can say it exists because of that shared past. Extrapolating forward using our equations, we predict that it continues to exist inside, continues to follow some trajectory deeper into the curved space. But those predictions, testing them through observation, the usual feedback loop we rely on in physics where we make a prediction and then check it against reality, that feedback loop is broken here. The prediction part still works, the testing part doesn't. There's also this question about whether the boundary itself changes when matter falls in. The equations say it does. Slightly. The mass inside increases, which means the radius of the event horizon increases slightly to accommodate that additional mass. So the boundary expands, in a sense, when matter crosses it. But we can't see that expansion happen in real time, at least not directly. What we see is matter approaching, fading, disappearing, and then, much later perhaps, once we've accounted for all the time dilation and redshift effects, we can infer that the boundary must have grown slightly. The growth is predicted, calculated, consistent with the equations. But observing it directly is complicated by the same effects that prevent us from seeing the crossing itself. Sometimes I wonder about the matter that's fallen in over the lifetime of one of these objects. All the gas, the dust, the stars that have spiraled inward and crossed the boundary, accumulated over millions or billions of years. All of that matter is still there, presumably inside the boundary, compressed into whatever configuration the equations predict near the center. But we can't see any of it. We can't distinguish between a black hole that formed recently and one that's been accumulating matter for eons, at least not by looking inside. We can measure the mass from the outside, calculate the size of the boundary, but the details of what's inside, the history of what fell in, when it fell in what order, all of that is hidden. The boundary doesn't carry information about its contents. It only carries information about the total mass, and maybe the rotation, and maybe the charge, but nothing more detailed than that. Everything else is sealed off. There's a phrase for this, something about how black holes have no hair, which is a strange way to put it, but I think it means they're simple from the outside. They don't have complicated features or markers or variations that would tell you about their history. Two black holes with the same mass, same rotation, same charge, are indistinguishable from the outside, even if they formed in completely different ways, even if they consumed different kinds of matter in different sequences. The boundary erases those details, or at least hides them so thoroughly that we can't access them. All the complexity of the matter that fell in, all the different states and configurations and histories, gets compressed into just a few numbers. Mass, rotation, charge. That's all we can measure from outside the boundary. And maybe that's appropriate, in a way. The boundary is, after all, the place where information stops being able to reach us. It makes sense that the details beyond that point would be inaccessible. We're left with the simplest possible description from our perspective. A dark region, a specific mass, a specific size. Everything else is inference, extrapolation, mathematical prediction about a region we can't verify. We're looking at the limit of what can be known through observation, and finding that the limit is geometric, enforced by the structure of space-time itself. By the way paths through space behave near extreme concentrations of mass. The boundary is real. The darkness is real. The region inside exists in some form. But the connection between that region and ours has been severed. Information flows one way, inward, and once it's inside, it stays inside. There's no path back. There's something that complicates this picture slightly, though complicates might be too strong a word. A prediction, or maybe an implication, that emerged from the equations decades ago. Something about how these boundaries might be less permanent than they first appear. Stephen Hawking worked through the math in the 1970s and found that when you account for quantum effects near the event horizon, when you consider how particles and antiparticles can briefly pop into existence in empty space, something strange happens. The boundary, according to these calculations, should emit radiation. Very faintly, very slowly, but emit nonetheless. The idea is that near the horizon, where space is extremely curved, particle-antiparticle pairs can form, and sometimes one falls into the boundary while the other escapes outward. From the outside, from our perspective far away, this looks like the boundary is radiating, emitting particles, losing energy. And if it's losing energy, it's losing mass, which means the boundary is shrinking very gradually, over unimaginably long timescales. Eventually, according to the math, the boundary would evaporate completely, though eventually here means timescales so long that they make the current age of the universe look like an instant. I'm not entirely sure what to make of this. The math seems sound, the prediction is taken seriously, but we've never observed it happening. These objects, the ones we can actually see, are all gaining mass, growing larger as they pull in matter from their surroundings. The radiation they might be emitting is so faint, so thoroughly overwhelmed by the infalling matter, that we have no way to detect it. So we have a theoretical prediction about what should happen, and the prediction seems consistent with everything we know about quantum mechanics and general relativity. But checking it directly, pointing at one of these boundaries and saying, yes, we see the radiation, we see it shrinking, that remains beyond what we can do. We just have the equation suggesting it should be happening. And if the radiation is real, if these boundaries do slowly evaporate, that raises questions about what happens to the information that fell inside. Information, as far as we understand physics, should be conserved. It should persist in some form, even if it gets scrambled or transformed. But if matter falls into the boundary, taking its information with it, and then the boundary slowly radiates away until it's gone, where did the information go? Did it come back out somehow, encoded in the radiation in ways we don't understand? Or was it destroyed, which would violate principles we thought were fundamental? There are proposals, ideas about how the information might be preserved, but they remain tentative, untested, impossible to verify with current methods. So we have this strange situation where our best theories predict something that contradicts other parts of our best theories, and we can't observe the phenomenon directly to see which prediction is right. The boundary seems permanent, seems to trap everything that crosses it forever based on the geometry. Yet quantum calculations suggest the boundary evaporates, suggest it eventually disappears. Both predictions come from well-established physics. Both seem reasonable within their own frameworks. But they're incompatible, or at least they seem incompatible. And resolving that tension might require understanding things about quantum gravity that we don't fully grasp yet. I keep thinking about how confident we were earlier, about the boundary being a permanent limit, about information being unable to escape once it crosses. And that's still true, as far as general relativity is concerned. The geometry still forbids outward paths. Light still can't climb back out. But when we zoom in to quantum scales, when we start asking what happens at very small distances near the horizon, the picture gets murkier. Quantum mechanics starts having a say, and quantum mechanics has different rules, different predictions, and the two theories seem to diverge at those scales, seem to give different answers to the same questions. General relativity describes the large-scale curvature beautifully. Quantum mechanics describes the small-scale behavior of particles beautifully. But where they meet, where both should apply simultaneously, things get uncertain. Maybe the boundary is more complicated at scales we can't observe yet, at distances so small, at energies so high, that our current theories start breaking down. Maybe there are processes happening near the horizon that blur the distinction between inside and outside in ways the equations suggest, but we don't fully understand. Or maybe the boundary is exactly what general relativity says it is, and the quantum effects are real, but don't fundamentally change the one-way nature of the crossing, and the paradox about information will be resolved in some way that preserves both pictures. I don't know. The uncertainty here feels different from the uncertainty about what's inside the boundary. That uncertainty is observational, geometric, enforced by the structure of space-time. This uncertainty is more fundamental, more about whether our theories are even asking the right questions at these scales. We're looking at a limit, but the limit itself might have limits, or at least our understanding of the limit has limits. The boundary exists. The observations confirm it. The darkness is real. But what the boundary actually is, what it means for information to cross it, whether it persists forever or just for timescales longer than we can comprehend, those questions touch on areas where our physics is still incomplete, where general relativity and quantum mechanics give different answers, and we haven't figured out how to reconcile them yet. The predictions become tentative, uncertain, dependent on frameworks we're still working out. The boundary is real, but the details of how it behaves at the smallest scales, over the longest times, remain unclear. We're at the edge of what the equations can tell us with confidence, and beyond that edge, there's speculation, proposals, mathematical possibilities that we can't yet test or verify or rule out completely. We started with something simple, the idea that when we let go of something it falls, and we can see where it went, that we can trace the path, that we can follow it if we need to, that the connection between here and there remains intact. We assume this constantly. We assume that space connects things, that light travels between places, that distance is something we can measure and confirm. We rarely stop to think about whether that assumption holds everywhere, whether there might be places where it stops working, where the connection gets severed in some fundamental way. And we've found such places. Regions where the geometry has curved so steeply, where mass has been compressed so tightly, that the paths light would normally take all curve back inward. The familiar relationship between here and there breaks down. Information flows in one direction only, and once it crosses a certain threshold, it stays on the other side of that threshold. The boundary exists. We've measured it. We've mapped its shadow. We've watched matter spiral toward it, fade, and disappear from view. But even after all of this, after tracing through the geometry, after understanding how the curvature works, after accounting for time dilation and redshift, and the way paths through space behave near extreme concentrations of mass, we're still sitting here, far away, looking at something we can't see inside. The darkness remains. The region beyond the boundary stays hidden, stays silent, stays causally disconnected from where we are. Calculating what should be there, extending the equations inward, making predictions about the curvature, about the density, about what happens to matter as it falls deeper. Those things are possible. Checking those predictions directly, though, verifying them through observation the way we're used to verifying things. The geometry prevents that. There's something almost ordinary about this limit in a way. It's geometric. It's based on how space curves near mass, how light follows those curves, how information propagates through curved space. These are all well-understood principles, at least in the regimes we can observe. The boundary is just the place where escape velocity equals the speed of light, where the geometry tips from one regime to another. A radius, a location, a threshold defined by mass and density and the equations that relate them. But the consequences of that threshold are, I'm not sure profound is the right word. Significant, maybe. A region of space that exists, that affects everything around it, that we can observe indirectly through its gravitational influence, but that remains beyond our ability to see into, to probe, to verify in the usual ways. The feedback loop we rely on is broken there. Predictions are possible, but testing them, confirming whether the extensions of our theories hold in that regime, the information we would need is on the other side of a boundary that only allows crossing in one direction. And maybe that's just how some things are. Some regions are observable, some regions are hidden. The boundary between them is geometric, enforced by the structure of space-time itself, by the relationship between mass and curvature, and the speed at which information can travel. We can approach it, study it from the outside, map where it is, and measure how it affects nearby matter and light. But crossing it means losing the ability to send signals back, entering a region that's causally disconnected from the one we occupy. The separation is imposed by geometry. We assume things fall and we can see where they went. We assume light connects us to distant places. We assume information flows both ways, that we can always check, always verify, always confirm what's happening somewhere else if we look carefully enough. These assumptions hold almost everywhere. They hold in our daily experience. They hold throughout most of the observable universe. They hold in all the regimes we're familiar with. But they have edges, limits, places where the geometry becomes too steep, where the curvature closes off certain possibilities. The boundary sits there, distant, surrounded by glowing matter that hasn't crossed yet. Light from that matter still reaches us, still tells us what's happening near the threshold. But the threshold itself remains dark, silent, a region from which information doesn't return. Matter approaches it, fades as it gets closer, and we can calculate the moment it crosses, based on its trajectory, based on the equations. But seeing the crossing itself, receiving confirmation from the other side, those things remain beyond what the geometry allows. The darkness is still there. Matter is still falling in, has been falling in for as long as these objects have existed. The region inside the boundary continues to exist, presumably, continues to follow whatever laws physics dictates in that regime, continues to contain all the matter that ever crossed the threshold. But we remain here, on the outside, looking at a region we can't observe directly, looking at darkness that stays dark because the geometry of space itself makes it so. We're still on the porch, still looking out at the night, still seeing the same stars, the same distant galaxies. But somewhere out there, scattered across space, are these regions where the rules change, where the connection we rely on to know what's happening somewhere else has been severed. Light falls inward. The future points in one direction. Information crosses a threshold and stays there. The boundary exists. We're here, watching. The darkness remains.